In we go to part 4 of function transformations. We're today going to look at the inverse of a relation. There's inverses all over the place in math. Basically, something that undoes what an original operation does. Subtraction is the inverse of addition. It acts oppositely to it. Division is the inverse of multiplication. So a function which takes in input and produces output has an inverse that turns that output back into the original input. One thing worth noting, and it's a very common misconception, is in regards to what f inverse of x means. It does not mean we are taking the reciprocal of f of x. That would be a multiplicative inverse. But a functional inverse essentially switches y and x. Again, it takes your output value, which is y, and produces your input value, which is x. Mapping-wise, we have this. So the point xy turns into yx. And graphically, this is kind of nice. For example, this point over here, which was originally 3 something, 1, 2, 3, 4, 5, 6, 7, would instead turn into the point 7, 3. Or this point here, which was at 1, 2, would instead turn into 2, 1. And this would be the same as we go along. So this point, negative 1, 4, would instead turn into 4, negative 1. Let's just make sure we connect these in the correct order. Feel free to do the rest of this as you wish. Negative 3, negative 1, negative 1, negative 3. So again, just swapping the x's and y's. So what, like negative 5? Right through those coordinates I drew, eh? And there we have it. Do you notice anything interesting about this transformation, looking at the new graph versus the original graph? Think about it for as long as you want. Feel free to pause this video, because spoilers are coming up. It's a reflection over a certain line. Now, we've looked at reflections over the x-axis and reflections over the y-axis, but this particular reflection is over something else. And in fact, can I make this dotted? I have no idea. Oh yeah, I can. Sure, that thickness will do. It's a reflection over the line y equals x. So an inverse, taking your xy points and turning them into yx, effectively reflects the function over the line y equals x. It is worth noting that not all inverses will necessarily be functions. Right? Like this particular one we had here, it is a function because there's no y value that's used more than once. Right? It passes the vertical line test. You can't draw a vertical line anywhere on here that hits the function twice. Super duper. But the inverse does not pass that test. It hits this like 3 times right over here. It's just ridiculous. So when we talk about a function inverse, we're not necessarily getting a function back, but we are getting an inverse. You could say that if a relation and its inverse are both functions, that it is 1-to-1. So for each x value, there's only one y value. For every y value, there's only one x value. Yes, that. So if you want to get these things algebraically, there's a whole bunch of ways. One way you could do this is describe what happens here and then undo it. So if f of x is 4x minus 3, that means we're taking x and we're multiplying by 4. And then we're subtracting 3. My writing looks like trash. What's going on here? Oh, that's what I want. Got it. So to undo that, we take the inverse of each one of these steps in reverse order. So this is step 1, step 2, step 3, right? Actually, realistically, that's 1 and that's 2. And to undo it, we'd first have to undo this. Oops, let's say add, subtract. Sorry, everyone, sorry. So to undo subtraction by 3, we add 3. And then to undo multiplication by 4, we divide by 4. What that can tell us is that f inverse of x means we take our variable, we add 3, because that's step 1, reverse order here, and then we divide by 4. This is kind of a weird way to do it. It leaves you with questions. So I personally would go much more algebraic, in which case I would swap x and y and then isolate the variable. So this one says determine the equation of the inverse of this function. There's no y in here, so we should start by saying that y is f of x. Then, that means that y is 2x plus 2, and thus, for f inverse of x, x is 2y plus 2. So here's that critical step, whoopsie daisy, that's an eraser, where we've swapped x and y. All of the occurrences of x turned into y's, all the occurrences of y's turned into x. And from here, we're isolating our variable. I'm just going to write this elsewhere. So isolating y, which should be on its own, says x minus 2 is 2y. And dividing everything by 2, we can say half x minus 1 is y. Technically, we're not done. There was no y in this original equation. There was an f of x, so we can talk then about f inverse of x, which replaces the y here, and that is half x minus 1. If you want, you can, on the side somewhere, just see what happens when you take f of f inverse of x. Just see what happens. You can do that on your own. Let me know if you find anything interesting. There are spoilers on the previous page. We're going to try this one as well. Now we're talking about something that's originally quadratic. So let's first determine the equation of the inverse, and then we'll deal with this second part and figure out what it means. It's very vibrant green. So again, you always have the freedom to pause before this thing goes. Any poops. So I've made sure I introduce y properly. Don't want to get that communication error. And then for f inverse, we swap x and y. And now we have to isolate y. Got to get it on its own. So I'll subtract 3 from both sides. I will, in a sense, take the square root of both sides, but of course, be careful here. That's a plus or minus square root. And that's from saying something like if x squared is equal to 4, then x could be plus or minus 2, because both of those squared to 4. So we're just taking that into account. And then moving on with it. So positive or negative root of x minus 3 is equal to y minus 1. And then with just a little bit of adding 1 to both sides, we can say that 1 plus or minus root of x minus 3 is equal to y. Technically not done, because we still have to put this back into function notation, since it was given in function notation. So f inverse of x is 1 plus or minus the root of x minus 3. That's this first part of this question done. This second part says something weird. What restriction could be placed on the domain of f so that its inverse is also a function? Interesting. Let's look at what's going on here. I'm going to take a moment and graph both of these with handy dandy Desmos. Work for me, Desmos, thank you. Our first function was this, minus 3, plus 3. I honestly don't remember. It was plus 3. That was our original function. And then when we took the inverse, instead of y equals all that stuff, it was x equals that. And we can see here that, sure, the original is a function. All quadratics are functions. But this one is its inverse is a sideways parabola. And then that one doesn't pass the vertical line test. It's definitely not a function. So the second part of the question... Oh, wait, can I just... I know how to do this. I got this. I think. Yeah, I do. Nice. So the second part of the question is asking what we could do to the domain of f so its inverse is also a function. The issue here is that we have a top half and a bottom half. And if we could just get rid of one of those halves, then this thing would be okay. But to get rid of one of the halves of this function, or this inverse of the function, we'd have to get rid of one of the halves of this thing. So as long as we say that this original parabola is only allowed for half of its existence, we chop away the other half, then its inverse will also be okay. So to make f inverse of x, that's really untidy. This quadratic has a vertex at 1, 3, so when x is 1, there's your halfway point. If we take half of that, we can take everything more than 1 or everything less than 1. We could just say x has to be greater than 1 if we want. There are infinitely many options we can actually put there, but if we say x has to be greater than 1, then this parabola gets cut off at the halfway point. The other half doesn't exist, therefore we won't have any issues with it trying to be a function. That is a kooky one, but questions like that have appeared on the provincial numerous times, and it's worth like 1 mark. It's just a straight up, what restriction can you place on the domain to make the inverse also a function? So if you can handle that question, super duper. Whoa, that's big. In any case, that concludes a bit about inverses. There is some practice work listed in the textbook for you. I recommend trying it. It's probably worth your while. As usual, if you have questions, comments, concerns, please do ask me. If you don't have questions or comments or concerns, then